very roughly, in the first half of the session, we're going to talk about some classic cryptographic tasks that, that have been studied in classical cryptography for 3 decades now, that we've developed the tools to do pretty efficiently. It's being deployed in industry at this point. And then in the second half, we'll see how quantum information can help make some of these tasks more interesting, reliant on weaker types of mathematical assumptions. And so we're going to talk about all that as we go along. If at any point you have any questions or want me to repeat something or go slower, please feel free to ask me to do that. Also, if you can't really, please feel free to move up if it helps to see the slides better. Yeah, and this, like I said, I want this to be very interactive, so please interrupt me if you have any questions at all. I'm also going to ask you guys questions, so please participate and try to follow along, and if you don't, interrupt. Okay, so let's get started. The topic of this first part is going to be secure computation. Here, the goal is simple. You have a bunch of parties that each have private inputs. In this case, you have a bunch of servers. They have inputs x1, x2, x3, x4. These could be entire databases. And these parties would like to compute a public function of these private inputs without revealing their private inputs to each other. So the only thing that they want to learn at the end of this process is the output of the function f applied to their inputs x1, x2, x3, x4. And none of these players should learn any information beyond this particular output. We're going to look at examples of this for certain types of functions later on in this lecture. But some of you have also probably seen this. But the general goal here is to enable untrusting participants to collaborate on private data. One other cryptographic primitive that's going to be pretty useful is what is called a one-way function. This is a function that is easy to compute in one direction, like breaking a glass, but hard to compute in the other. What do I mean by hard to compute in the other? If I sampled a random input and evaluated the function on this input to get an output y, and then I gave this value y to an adversary, then the probability that the adversary, given such a y, would be able to find a pre-image would be negligible. Okay? So given such a y, it's hard to find any x such that f of x equals y. This cryptographic primitive is going to come in useful later on. We'll see how. But now I want to move on to another cryptographic primitive that's going to be the focus of both of these two talks, like the first version and the first part and the second part. And this is what is called oblivious transfer. So this is a two-party primitive where Alice has private inputs m0, m1, and Bob has private input b. So recall that we said secure multiparty computation allows multiple players who don't necessarily trust each other to compute some function on their private inputs. This is a special case of that, where one player has two inputs, messages m0, m1. The other player has input b. And Bob would like to learn the bth of these two messages without revealing to Alice which one he wants to learn. Okay, so Alice and Bob interact with each other. Bob sends input B into this interactive protocol. Alice sends inputs M0, M1. And at the end, Bob is supposed to recover MB. Alice doesn't really recover anything, so we'll just denote this by bottom. And the security property at a super duper high level is that Bob doesn't learn M1 minus B, which is the other message that he did not choose to get, and Alice doesn't know which of the two messages Bob learned. Okay, so this may seem fairly non-trivial. Alice cannot send Bob both messages because then that means Bob learns both. That's not allowed. Bob can't tell Alice which one he wants because that's not allowed either. Alice shouldn't find out which one he wants. So this at first seems highly non-trivial. Before discussing how to build this, let's discuss what it means for an oblivious transfer protocol to be secure. Security is defined by assuming the existence of an ideal or trusted party. And imagine that to this party, Alice could send her inputs M0, M1, and Bob could send his input B. And this party was trusted by both of them, so they were okay with the trusted party learning all their inputs. Then this trusted party would send Bob MB and would send Alice bot, indicating that the protocol is over. Okay, so that's what would happen if there existed an ideal or trusted party that they both trusted with their inputs. How do we define security when imagining such an ideal party? Well, we say that, one second. We say that the only information that Alice and Bob would learn when interacting with each other in this interactive process is something that they would have learned in this ideal process where they don't really learn anything. Bob only recovers MB and Alice only recovers bottom. So let me try to make that more precise in a second. Before that, let's just talk about a very simple way to try to construct oblivious transfer. And this is using public key encryption schemes. So a public key encryption scheme you've probably heard about before in this series itself allows Bob to send 2 public keys to Alice and keep their corresponding secret keys with himself so that Alice can send Bob, Alice who has messages M0, M1, can encrypt each of her messages under each of these public keys and send them to Bob. Now, suppose Bob were able to sample these 2 public keys in such a way that he only knew one of the secret keys, specifically the bth one, and did not know the other secret key. Then it would be possible to use this type of a protocol to build oblivious transfer because Bob would only know sk sub b and would not know sk1 minus b. And again, I'm not suggesting that you can use any public key encryption scheme here, but if you had an encryption scheme with the property that you could sample a pair of public keys and know the secret key corresponding to only one of those keys, then Bob could send both these keys to Alice, and assuming that the 2 keys are indistinguishable from each other, Alice wouldn't learn which of the 2 secret key corresponding to which of the 2 keys does Bob hold. And at the same time, Bob would be able to recover M sub b as a decryption of the bth ciphertext under PKB. Sorry, under the secret key that he knows. The problem is that if we had Bob that was trying to act maliciously, then perhaps for many such encryption schemes, it's going to be possible for Bob to sample both public keys in such a way that he knows secret keys corresponding to both of them and he recovers both messages, thereby breaking security. So this brings us to a discussion about the types of possible adversaries that we need to care about. The first is a semi-honest or honest but curious adversary. This is one that follows protocol specifications, samples randomness the right way. So if it's asked to sample these 2 public keys in such a way that it only knows the randomness corresponding to one of the secret keys, then this adversary does that. The other is a malicious adversary, which does not follow protocol specifications. And we're going to try to define what it means to be secure against malicious adversaries now. So recall that we said that in an ideal interaction, Alice would want to send both her messages M0, M1 to a trusted party. Bob would send his bit B. This trusted party would return M sub B to Bob and return end to Alice. And the goal of MPC is to remove the need for this ideal party. So get the same security properties as you would get against each other if you had this ideal party present, but run a protocol that does not actually need any ideal parties in it. So what that means is Alice sends M0, M1 into a protocol, Bob sends bit B, they interact back and forth a bunch of times, Bob recovers MB, and more importantly, on the left protocol where there's no ideal party, Bob, from his interaction with Alice, in his view, gets no more information than he would have obtained had he been interacting with this ideal party. And note that in its interaction with the ideal party, Bob only sends B and gets back MB. So at first, it may look like something weird is going on here, right? Bob's view or state at the end of his interaction with the trusted party is literally just send B, get M1 minus B. On the other hand, on the left, we're saying, well, there's some protocol. For example, Bob is sending a bunch of public keys, getting a bunch of ciphertexts, decrypting, blah, blah, blah. So there's some other protocol that's more complicated than send B, get M1 minus B happening. And we're trying to say that these two should look the same to Bob. So there's something weird here. Yes? Sorry, can you? Oh, sorry, get MB. Thank you. Sorry, this should have been get MB. Thanks. Right, so in the game on the right, Bob's state is literally I sent B, I received M1 minus B. In the game on the left, he's doing a bunch of other things. These games are clearly not the same game. They look very different. And yet, to define security, we want to say that from Bob's perspective, they actually look pretty similar. So what that means is we need to define an interface between Bob and the ideal party. And so note that the difference from above is that we're inserting this interface. This is typically called a simulator. And the simulator's job is to make it appear to Bob as if he were interacting with Alice. And additionally, make it appear to the ideal trusted functionality as if it were interacting with Bob. So what that means is the simulator is going to be the one sending B and getting back MB. And now, given this information, the simulator's job is going to be to generate a state or a view for Bob that is indistinguishable from Bob's view in their interaction, or in Bob's interaction with an honest Alice, where Alice had messages M0, M1. Bob is arbitrarily adversarial, so he does anything he likes in this protocol, behaves arbitrarily. And at the end, gets some, let's call this, gets a state. Let's call this, let's say this is a mixed state. So let's call this row real. This is Bob's state at the end of the real protocol. Let's denote by row ideal the state that Bob ends up with in its interaction with this Superman guy, the simulator. Okay, so yes. Sorry, what was the question?
Isn't that stupendous man?
That is stupendous man, yes. Yes, that's right. But we'll call him simulator for the purposes of this lecture. Okay, cool. The reason that we're defining this simulator is because this will be a really useful tool in analyzing protocols and proving that they're secure. So what we're going to do is we'll build a protocol, and then we'll show that for every adversary that possibly corrupts Bob, there exists a simulator. And what the simulator does is it generates a view for Bob, row ideal, while the only thing it's allowed to do is, to the trusted functionality, to the ideal party, is to send the bit B and receive MB. And from this, it generates a view for Bob such that the trace distance trace distance delta between rho real and rho ideal is small. So how small? We'll typically say that this should be a negligible function in n. A negligible function is one which is smaller than the inverse of every possible polynomial. So example is like 1 over 2 to the n by 2. And this is going to be an asymptotic definition, so we'll require that for large enough n, it should be the case that this trace distance grows negligibly. Let me make sure that you have seen the definition of trace distance before, but let me remind you what it is anyway. So this is half trace rho real minus rho ideal. And forgetting about like the exact definition for a second, the operational meaning of this is that this is just the maximum probability that any measurement can distinguish the mixed state rho real from the state rho ideal. Okay? Okay, any questions about indistinguishability or simulator, stupendous man? Okay, cool. So if not, then let's move on to defining what it means to be secure against malicious senders. Now this time Alice is the one that's malicious. And again, we want that Alice's view in her interaction with Bob, even though she's malicious, so she may not even be sending two messages M0, M1, she just behaves arbitrarily on the left, whereas Bob is honest this time, so he uses a choice bit B. Her interaction on the left should be indistinguishable from the one on the right, where on the right, what she's supposed to be doing is send M0, M1, and then get protocol ended. Okay? And actually, it's not just, for technical reasons, it's not just the state of Alice on the left that we want to be indistinguishable from her state on the right game. We actually also want that the joint distribution of Alice's state together with the output that Bob obtains, which in this case is M sub B, should be indistinguishable. So again, just like before, these look very different. So as you can see, Alice on the left is doing things like getting public keys from Bob, for example, encrypting her own messages, sending them. So it's very different from just sending M0 and M1. In fact, clearly, if she were to just be sending M0 and M1 to Bob, that would be ridiculously bad because Bob should learn only one of the two. So these are very different protocols. And for the same reasons as before, we will introduce the interface on the left, the simulator, whose job it is to pretend to be Bob in the interaction with Alice, and to make it so that Alice's state in the interaction on the left is indistinguishable from her state in the interaction on the right. Whereas the simulator pretends to be Alice, sends M0, M1, gets bought, Bob sends B, gets MB. Okay? And we require that Alice's state, rho real, Alice, the trace distance between Alice's states in the two games is small. And let's just try to understand and reflect on what that means for a second. That means that if you look at this ideal game, there is no way that Alice learns any information about the bit B in the ideal game. Why is that? Because Alice's view is being generated entirely by the simulator. And the simulator only gets to send M0, M1, and that's it. Simulator has no idea what the bit B is. So in the right game, Alice's view simply cannot contain information about the bit B. And that means on the left game also, because these two views are very close, the left view also should not contain information about the bit B. Okay, so delta, rho real, rho ideal is negligible. Okay, so hopefully these real ideal definitions are clear, more or less. Now, again, something must seem off at this point. It's looking like the simulator, on interacting with Alice, is able to easily find both her messages M0, M1 somehow, and send them along to the ideal functionality, to this ideal party. But on the other hand, Bob, in his interaction with Alice, should only learn one of the two, should learn like either M0 or M1, but not both. So there seems to be a bit of a contradiction here. How on earth is the simulator going to be able to find both when Bob cannot? And that's why the simulator is stupendous, man. The simulator has some extra powers that Bob does not. And in particular, you've seen one of these in yesterday's talks. This is called rewinding. A simulator is a program that has access typically to the adversary's entire piece of code, which means it can run this code forward and backward and forward and backward as many times as it likes. On the other hand, Bob, who's interacting with Alice, can never go backward in time. They just keep going forward. If Bob makes a request, hey, I want to go back to that point, let's rewind, and Alice will say, this is ridiculous, I'm not going to do it. But the simulator has this power because it has access to the code of Alice. So just going forward, it will be good to keep in mind that the simulator is usually going to be able to rewind or do other interesting things that an actual real party like Bob cannot. And that's where these simulators' abilities to generate these types of simulated views will come from. Yes?
Are you going to be looking for both of these distance requirements are statistical, basically, right? They don't have any computational statistical?
Good. Yes. So for now, I haven't really defined computational versus statistical, but for the most part, we'll only care about statistical, but at some point we will have to talk about computational notions. So that was a good question. Let me just repeat the question and answer it. This measure of distance between the two distributions, here we can talk about how distant the two distributions are to an unbounded adversary versus how different they appear to a computationally bounded adversary. So a computationally bounded adversary is going to be one that runs in polynomial time, and the requirement in that case will be that no such bounded adversary can distinguish between the two distributions, meaning the probability that a computationally bounded quantum polynomial time distinguisher on input rho real outputs 1 minus the probability that it given rho ideal outputs 1 for all quantum polynomial time distinguishers. This should be negligible. So that's the computational notion. Okay. And the one written up here is the statistical notion. So I am going to switch to computational at some point because we do need to use assumptions. And if you, okay, we'll get to that in a bit. Does statistical versus computational make sense? Like this is basically saying the same thing. The box is saying the same thing as the line below, except it's saying that for every distinguisher, no matter what time it runs in. And the line below says, as long as the distinguisher is a quantum polynomial time Turing machine or a quantum polynomial sized circuit, it should not be able to distinguish the two distributions. But if it got more time, maybe it could. So the computational notion is just weaker. Okay? Thanks, Chris, for, yes?
I have one question. So I was trying to just think about what the inputs are to the simulator.
Yeah.
I'm guessing the program of Alice is one input, including the inputs. Does it also take as input Bob's program without the input?
No, so it does not. But in this case, Bob is honest. So Bob's program can be thought of as public. So it can, basically. This is a public program.
But it doesn't have the input?
It does not have the input of Bob, yes.
Because otherwise you need something about the distribution.
Exactly. So for all purposes, it's good enough to think of the simulator as getting access to Alice's program, usually just in a black box way, which means it goes forward and backward, is able to rewind. And that's it, actually, in this case. And then it must send M0, M1 out somehow. And these actually need to be the correct M0, M1 that Alice was using in her actual interaction with Bob. The reason that that needs to be the case is because Bob gets MB in both these games, and that we also need that to match across both games. All right. So let's now move on to try to constructing this thing. Yes? Yes?
So does the security get weakened if we are required the program explicitly and not just as a black box for Alice to construct the simulator, or it makes no difference?
Great question. So the question is do we really need to restrict things so that the simulator only gets access, black box access to Alice's program? Or is it a weaker notion of security if we give the simulator Alice's program to look at? Now, we can, and these are called black box versus non-black box simulators. Non-black box simulators typically do get access to the code of the adversary. It is the same meaningful notion of security, except that the simulator has somewhat more capabilities. But not really, no. The problem that the reason we usually work with black box simulators is because in general, the code of Alice could be arbitrarily scrambled, obfuscated. It's not clear how to use it usually, except via black box access. Now, there are methods to do that, to use codes in non-black box ways, and they do give very interesting results, but there are very limited methods. So most of the stuff we do is black box access. Okay. All right, so now let's try to build this thing finally after like a whole array of definitions. Let's try to understand how to build this. So the first thing that I'm going to introduce here is a random oracle. So you've seen this yesterday in quite some detail. We're not going to be talking about quantum random oracles today. So this is just a classical random oracle. And the way we will build an OT, this will only use classical communication and classical cryptography entirely, but we'll just get a flavor of how this is built in the classical setting, and then see interesting ways to do this also in the quantum setting. So the way this is done classically is, let's have Bob generate two public keys, PK0 and PK1, but in a very specific way. The way Bob does that is he first samples. So Bob has choice bit, input bit B, and Bob should be able to sample SKB and PKB in such a way that he knows the Bth secret key, and then he should also have another public key, PK1 minus B, for which he does not know the corresponding secret key. So the way this is done with the help of random oracles, and this is a recent work of Masny, Rindal, 19. And let me also say here that this follows a long line of works that build OT, starting with El-Gamal, Naor, Pincus, Kalai, Halevi, and Mikert. So there are a bunch of constructions that I'm not going to talk about because they require more background that you guys haven't seen before. I'm choosing to talk about one that uses random oracles because you know what they are, and generically public key encryption schemes with some very generic properties. Okay, the idea is for Bob to sample two public keys in such a way that he knows one secret key and does not know the other. How do you do this with the help of random oracles? Well, let's make it so that Bob samples S0, S1. Let me say that differently. Bob on input a bit B samples S0 uniformly at random, and then set S1, actually. I'm going to run out of space. Sample SKB, PKB, so that he knows the Beard secret key. And now sample S0 uniformly at random and set some S1 to be hash of S0, where hash is computed using the random oracle, XORed with PKB. So what happened there was Bob sampled a public key secret key pair first. Then he sampled a uniformly random string S0, hashed it, and set a different string S1 to be hash of S0 XORed with PKB. And now Bob should simply send S0 and S1 over to Alice. Okay. What Alice does given these is she computes PK0 as hash of S0 XORed with S1 and PK1 as hash of S1 XORed with S0. Okay. So Alice now comes up with two public keys given these two S values which appear completely random to her, and then encrypts both her messages. So Alice had inputs, remember, M0 and M1. She encrypts both her messages using each of these public keys. And sends the resulting ciphertexts over to Bob. Now in this case, Bob sampled S0 and S1 in such a way that he knows, SK sub B. Maybe let me rewrite this a little bit so that it's a sample SKPK, and this is right. Yeah, let's make it a little bit easier. So Bob starts off with just sampling S0 and S1 such that S1 equals hash of S0 XORed with the public key for which he knows the secret key. He sends S0 and S1 to Alice. Alice uses them to come up with two public keys. One that is the hash of S0 XORed with S1, the other that is the hash of S1 XORed with S0. Encrypts her messages using each of these two public keys and sends the resulting ciphertexts to Bob. Yes, sorry.
It seems like Bob isn't using bit anywhere. Is he swapped that?
Yes, I'll get to that in a second. Yes. Good. So Bob knows the secret key corresponding to, in this case, PK0, which is hash of S0 XORed with S1. So Bob can decrypt CT0. Okay. So far, we haven't used Bob's choice bit anywhere. We just built a protocol where Bob always gets the first message that Alice sends. How? Well, he set S0 and S1 in such a way that he knows the secret key for hash of S0 XORed with S1. But now, there's a simple tweak to this that makes it so that Bob can recover either of the two, which is, if Bob's bit is 0, then he sends S0, S1 as is. If B equals 0, let me write it. If B equals 1, Bob sends S1, S0. Yes?
Couldn't we have produced two pairs of private and public key and send both S0, S1 and S0 plus whatever public?
Right, so let's get to security in a second. First, let's talk about correctness, and then I'll answer your question. So it's a great question, but I'll get to it in a second. Was there a question?
Yeah, I guess I'm wondering are you sacrificing some of the ability in the ideal scenario to, if you're interacting with a trusted party, then theoretically Alice could send her messages to the trusted party, and then after that, Bob could, send his choice bit B to the trusted party. But here it's almost like Bob is initiating the protocol by first
Right, so one of the goals here is to not have a trusted party in our construction. We want a scheme which does away with the need for any trusted party. We only introduce the trusted party when trying to argue what it means for the protocol to be secure. Then when we talk about security, we say they learn no more than they would have learned had they just been interacting with the trusted party. On the other hand, the actual protocol should not rely on any trusted parties at all, because the goal is for a bunch of players to compute on their inputs without having to send them all to any centralized trusted player. So yes?
I think the question you might have been asking is, like, if you think about how the security group might go here, here Bob is sending over this S0, S1, and maybe Alice sees those and like adjusts her messages to depend on S0, S1 or something, right? Is that what you're getting at?
Yeah, I guess, I mean, it might not make a difference. I think your explanation also helped, but I guess I'm kind of picking up on the fact that maybe it doesn't matter in the grand scheme of things that Bob is initiating this protocol with the decision he's making based on his choice of me before, like, Alice has done anything. So that's kind of
Good, yes, so that's a very valid concern, and I think, yeah, I think I see what you're saying. You're wondering if Bob's choice of S0, S1, somehow, which does encode the bit B that he has, can somehow influence Alice's choice of the messages M0, M1, which in the ideal case, that should not be the case. Alice's messages should be completely independent of Bob's input. It turns out here that because S0 was sampled randomly, and then S1 was set as hash of S0 XOR PK, just the randomness of the random oracle plus the randomness in setting S0 makes it so that S0, S1 are actually random, subject to the fact that they both, actually they're just uniformly random. You need to make some additional assumptions from the specific public key encryption scheme, which is that the public keys are indistinguishable from being uniformly random. But under that assumption, PK is indistinguishable from uniform. Under that assumption, S0 and S1 appear to Alice as if they were just two uniformly randomly chosen strings. And whether they're sent in order, like S0 first, S1 next, or reversed, Alice can't really tell the difference. So, yes?
PK was the randomness of the order to make S1 correctly random.
Not given S0. Yeah. Okay, so, all right, so let's first look at correctness, right? So can Bob always recover the Bth ciphertext? Let's work through it. So let's say B was 0. Then Bob knows the secret key corresponding to PK0, right? Because that's how he set S0, S1. And so Bob knows SK0, which means he can decrypt the CT0 ciphertext to get message M0. On the other hand, if Bob's bit B was 1, now Bob has sent S1, S0, which means let's call what Alice receives as T0, T1. So in this case, Alice's public keys are flipped, and now Bob knows SK1, which implies that he can decrypt CT1 to get M1. Okay, the argument is quite simple. It's just saying you flip your S0 and S1, and that flips which key Alice puts her Bth message in. Okay. So, now I'm just going to give you an intuition for security here. Sorry, yeah, I'm just going to give you an intuition for why this is secure without actually going into the formal security proof. We'll look at more formal security proofs for some of the quantum schemes we introduce. One of the main things I want to point out about this scheme is that even with the use of random oracles, we're relying on public key encryption schemes that satisfy certain additional properties. So to build oblivious transfer in the classical setting really requires advanced forms of public key encryption schemes. What we're going to be able to do in the quantum setting is not use public key encryption at all and use cryptography that is known to be much weaker, just in terms of the amount of hardness it provides. Or in other words, it's possible that public key encryption just does not exist. Like all public key encryption schemes are broken. And yet, using quantum information, we'll be able to build oblivious transfer schemes that will remain secure under assumptions that do not break down even if all public key encryption schemes break down. So that's one of the things we'll discuss a little bit later. For now, coming back to this protocol, let's talk about the security for a minute. From Alice's perspective, if the public key has this property that public keys are close to uniformly sampled strings, so a randomly sampled public key is computationally indistinguishable from a uniformly random string, then Alice cannot tell whether she got S0, S1 in the right order or swapped around. And as a result, she doesn't know what Bob's bit B is. On the other hand, why does Bob not learn both of Alice's messages? Well, again, one needs to use some random oracle proofs here, which I don't have time to get into, unfortunately. But the overall idea is that when Bob queries the random oracle to get hash of S0 and sets S1 to be hash of S0 XOR PK, one can actually show that the probability that he also knows the secret key for the other public key, which like switches out S0, S1, so which is hash of S1 XORed with S0, this probability is really small. So one can prove that if Bob could come up with an S0, S1, for which he knows the secret key corresponding to both hash of S0 XORed S1 and hash of S1 XORed S0, then Bob can break security of public key encryption schemes or the security of random oracles. So it's a little bit of a delicate proof. I'm not going to get into it. Just want to give you a sense of what these constructions look like in the classical setting. Yes? T0, I just called what Alice received T0, T1. Let me clarify. So Bob sends Alice T0, T1, where if B equals 0, then Bob will set T0 to be equal to S0 and T1 to be equal to S1. If B was equal to 1, Bob will flip them both. Hopefully that clarifies it. So, okay. So now suppose that this object, oblivious transfer, existed. I now want to tell you why we've been focusing and talking about this object for such a long time. And in particular, I want to talk about how to securely realize many different specific functionalities. So F between Alice and Bob, where Alice has private input X, Bob has private input Y, and they'd both like to end up with F of X comma Y. And F here is the XOR function in this first example. And they'd want to do this in such a way that the only thing Alice learns at the end of this interaction is her own input, which she always had, and the output of the function on her and Bob's inputs. So, which is just, in this case, X XOR Y. Okay, so this is a really interesting function. This function has the interesting property that Alice's own input, X, along with the output X XOR Y that she gets, reveal to her what Y is. This just gives you perfect, full information about what Y is supposed to be. Why? So actually Alice, given her input, which is X, and output, which is Y, sorry, not Y, which is the XOR of X and Y, can always find Y, which is the entirety of Bob's input. How do you find it? You simply XOR the input and the output together. So in the special case of XOR, a very secure protocol to compute XOR against the weaker class of semi-honest adversaries that behave according to protocol is for Alice to send X to Bob and Bob to send Y to Alice, because they were going to learn that from the output anyway. So it's okay to just send your input across to the other party. Now, this is not going to be the case for the next functionality that we look at, which is secure AND. Now, suppose Alice has input X, Bob has input Y. These are bits, and they'd like to learn the AND of the two bits, X and Y. In this case, the output does not necessarily reveal the other party's input in its entirety. So Alice would like to learn X and Y, and so would Bob. Unlike the case of XOR, it's not okay for both parties to send their inputs across to each other in the clear. Why is that? Because then the protocol would reveal a lot more than just the input and output. And recall that if there was an ideal party that they were sending their inputs to and getting outputs from, then the only thing that they would learn is their own input and then the final output. Okay? And it's easy to see why this is the case for AND. So let me just draw the truth table here. You have A, B, A, and B. Let's just look at this particular row, for example. So when Alice has input 0 and Bob has input 1, then Alice's output, which is A and B, which is 0, actually does not tell her what Bob's input was at all. Right, so how do we realize AND securely? It's not clear. Sending inputs is not okay. And this is why we developed this tool called oblivious transfer. Suppose Alice and Bob had access to that oblivious transfer protocol. Then they can pick their inputs for the oblivious transfer protocol in such a way that the output of the OT, oblivious transfer protocol, is going to give them both the output X and Y. Let's try to again assume that Alice and Bob will stick to protocol, which means if you ask Alice to take her input, compute something on it, and then send the result to Bob, she will actually do that. Can you think of some way to set Alice's inputs M0, M1 into an OT in such a way that Bob computes his bit B as some function of Y. Alice computes her M0, M1 values as some function of X in such a way that at the end of this, what Bob gets is M sub B, which should be X and Y. Any ideas on how Alice can set M0, M1, and Bob can set B so that Bob ends up with X and Y? Maybe give you a hint. Let's say M0, we set it to X and 0. And let's say we set M1 to X and 1. Okay. Now, Bob can set B to just be equal to Y. And now, just by the way we set M0 and M1, Bob gets, if B is 0, Bob gets X and 0. If B is 1, Bob gets X and 1. And so Bob gets X and Y. Sorry? Would this not work for any binary function?
Yeah, like you could just say f of x, 0 and f of x, 1 and
perfect, yes. For any binary function, you could, it doesn't need to be and, you could just set m0 to be f of x comma 0, m1 to be f of x comma 1. Bob would obtain f of x comma y. Okay. Now, the reason this is interesting, I'm out of time, so I'm going to skip a little bit here. Yeah. The reason this is interesting is that any general Boolean function, any general Boolean circuit with many, any general circuit can be written as a Boolean circuit, which is a collection of AND, XOR, and possibly NOT gates. So, and so any function that Alice and Bob may want to compute on their inputs can always be represented as bit strings, and the function can always be represented as a set of Boolean circuits, one circuit computing every bit of the output of the function, and such that Alice and Bob can now evaluate these different circuits on each of their inputs gate by gate. So we'll talk about that in a little bit. The idea is going to be that some input wires in this circuit are going to come from Alice. Some other inputs are going to be set by Bob. They will never have to share these inputs with each other. And yet, just by using OT, they will be able to evaluate all these gates one by one, again, without revealing any intermediate values, and finally only recover the output of the computation. So now let me give you a little bit of, let me give you an idea of how that's done. To start with, some of you may already know this word. This is secret sharing, and if you don't worry about it. It's one of the simplest, one of the most basic concepts in cryptography is the idea of sharing a secret A into two parts, A1, A2, such that the two together reveal complete information about the secret A, but individually look completely random and independent of the secret A. So such that A1 XORed A2, the way this is typically done, is by computing random. So given a secret bit A, you sample random A1 and A2 such that they XOR to A. Okay? We're just going to use this. So to begin with, Alice, let's say, has input X. This can be not just a single bit, but a long sequence of bits. Bob has his own input Y. Alice shares her input into XA, XB, two parts, sends XB to Bob. Bob shares his input into two parts, YA, YB, and sends one of these parts to Alice. And by subscript A, I'm denoting the parts, the shares that go to Alice. So at the end of this, Alice has shared XA of her input and YA of Bob's input. And Bob has shared XB of Alice's input and YB of his own input. So let's just remind everyone that Bob's input is Y and Alice's input is X. Okay, so this is how they set things up. In the beginning, let's say Alice and Bob are trying to compute some arbitrary function on their two inputs, X and Y. To begin with, they're simply going to secret share these inputs. And Alice will send one of the shares of her input to Bob. Bob will send one of the shares of his input to Alice. And now they each have one share of the inputs. Now, given these shared inputs, they can actually compute individual gates on them in the following way. Again, to begin with, Alice has XA, YA. Bob has XB, YB. The goal now is to end up with shares of the output. So suppose the function f is the XOR function. We want them to end up with shares of f applied to x and y, where x is XA XOR XB, like combine their two shares, y is YA XOR YB, and you want them to end up with this. Now this is really simple. So the way you can do this is simply Alice adds her own shares up, XORs her own shares, Bob XORs his own shares, let's call the result dA and dB. Note that dA and dB together XOR to X XOR Y, so these are shares of X XOR Y. Okay. Now, this is the easiest case. Let me move on to the more interesting example, which is AND. Now, again, what do we have? We begin with a setting where Alice and Bob have shares of two inputs, X and Y. What they want to do is compute the AND of X and Y, which is nothing but the AND of XA XORed XB and YA XORed YB. Okay? And they want to end up with shares of the result. So end up with, let's say, dA and dB. Okay. They want to end up with dA and dB such that dA XORed dB is this value. Okay, does the goal make sense? Okay. So Alice should at the end have such a dA and Bob should have dB. Now can you think of how to do this with OT again? So let's say Alice and Bob have access to OT boxes. Alice has XAYA, Bob has XBYB. They'd like to be able to compute this value dA and dB that satisfy this relation. And let me actually open this up. So this is nothing but XA and, I'm just going to use the logical AND symbol now, XA and YA XOR XB and YA XOR XA and YB XOR XB and YB. Okay, so this is distributive, so I can open it up and write it down this way. Now, Alice has both XA, YA, so she can compute XA and YA locally, right? So this is something, XA and YA is something Alice can compute locally, given what the information she has. Similarly, Bob can compute the XB and YB part of this locally, given the information he has. The problem are these cross terms. One is of the form XB and YA, the other is of the form XA and YB. But these are also just ANDs. And we know how to do AND with OT. We just saw, like, set the first input to be XB and 0. Alice sets the first input to be XB and 0, the second input to be XB and 1, and Bob inputs YA into the OT. Now that by itself is not entirely secure because the problem is we don't want to actually reveal XB and YA to Bob. So we're going to do something very close, but just a little bit different. So let me just show you what that is now. Okay, so now what we have is we want to compute XB and YA XOR XA and the way to do this is to run two OT protocols. One into which Alice sends XB and 0, XB and 1, and Bob sends YA. The other into which Alice sends XA and 0, XA and 1, and Bob sends YB. Now Bob gets XB and YA, and here Bob gets XA and YB.
Alice doesn't know XA.
Oh, sorry. You're right. Alice doesn't know XB. Sorry. Thank you. Alice knows YA, so she should be setting this to YA and 0. Bob inputs XB and gets. You're right. Thank you. Right, Alice has all the A shares, so you run these two OTs. And now the one other thing that we add to this is some randomization. So what Bob gets is not the AND, but the AND XORed with a random bit. And now Alice knows what this random bit is because she's the one who set it. So she sets her DA is going to be XA and YA XORed with this random bit R1. And there's going to be another random bit used for the second OT, XORed with R2. So let me just shade. Alice's DA will look something like this. And Bob's share DB is going to be XB and YB. So DB will be XB and YB, XORed with O1, XORed with O2, where O1 and O2 denote the outputs he gets from these two OTs. And now it's an easy check that if you add these two shares up, if you add everything up, you get XB and YB, XOR XA and YA, XOR R1, R2, XOR R1, R2, which cancel out, because if you XOR a bit twice, it just gives you a 0. And then you have XOR XB and YA, XOR XA and YB. So what you've ended up with is exactly this term here, XA and YA, XB and YB, XORed with all these values. Okay, so this is basically just a bunch of calculations. There's nothing very deep going on beyond just the fact that you can use OT to realize Boolean functions. And you can also do so on secret shared inputs. So even if Alice doesn't have all of X and Bob doesn't have all of Y, they just have secret shares of these inputs, you can still do it. Okay. Similarly, you can do NOT. NOT is extremely easy. If Alice and Bob have shares CA and CB of some input C, and they want to compute the NOT gate on this C, then Alice just can flip her share. Of course, many of these protocols are assuming that Alice and Bob do as they're told. Now, there are ways to make sure that if Alice and Bob deviate from instructions, for example, if they were to evaluate an AND gate, a NOT gate, and Alice was supposed to flip her share, and let's say she just doesn't do it, there are ways to detect that. And again, that's not something I'm going to be talking about in a lot of detail. I just want to give you a sense of how oblivious transfer protocols can be used to evaluate arbitrary general circuits on secret shared data. So for example, in this case, Alice starts out with inputs XA, YA. Let's say this wire W1 is X, W2 is Y, W3 is A, W4 is B. And Alice has shares, the A shares of all these inputs. Bob has the corresponding B shares. Then what we've already looked at suffices to evaluate these circuits securely. And the way that is done is, well, this is nothing but an AND gate. So run the AND protocol that we just saw to get shares DA and DB of X and Y. So similarly, run the XOR protocol, which is even simpler, just add your shares up, to get shares of E, which is A XOR B. Now that you have shares of the inputs to both wires of the next XOR gate, run another XOR to get F, which is D XOR E. So, and you get, they both end up with shares of F. One of the things that you need to be a little careful about is randomization. So just a second. But you can ensure that at the end, Alice and Bob each end up with shares FA and FB of the output, which I'm denoting by F. Maybe not a great use of notation, so let me call it G. So they end up with G computed on X, Y, A, B. And they actually end up with shares. GA, GB of the output wire. Okay. And this is just repeatedly applying the protocols that we've already seen. Like you start with shares of input wires. Let's say it's an AND gate. You run the AND protocol. You end up with shares of the output wire. And so that's what you do for this first gate right here. Now, for the gate below, do the same thing. Again, you end up with shares of the output wire. Now, these output wires are nothing but input wires to the next level. So repeat the same thing for the next level and keep going. And there was a question, yes? Right. Okay, yes, so good question. So the question is, it looks like Alice and Bob need to keep talking to each other many times back and forth. Every time they need to evaluate a gate, they need to run an OT, which involves some communication, some interaction. So the number of rounds in general will grow, at least with the depth of the circuit if you did this. And that's not ideal. There are ways to get around it. And in fact, by now we know pretty tight, round, optimal ways to evaluate classical circuits. Basically Alice and Bob need to speak just one time, and that suffices. So we know how to do that. That's more complicated, involves more crypto machinery and gadgets, so I'm not going to talk about it, but that's a whole area of study. So, yeah. What I want to convince you of right now is that OT is a pretty useful tool. The fact that you can use it to do and then in general, you can also use it to do NAND. So another way to think about circuits is that NAND gates are universal. So you can build any circuit with just NAND gates. And then that's it. And all you need is OT. And that will give you a way to evaluate any general circuit on secret shared data. And what I've shown you is a way to do it, assuming that the adversaries behave somewhat honestly, stick to protocol. But you can, in fact, make these protocols using some additional techniques. You can also make them secure against malicious parties. And where security against malicious parties for general functions is defined the exact same way as it was for the case of OT. So for a general function f, again, Alice sends her input x to an ideal party, or maybe honest Alice interacts with a malicious Bob. This party simply expects inputs from both players and generates outputs for them both. These may not even be the same function that is sent out. So f can actually be two different functions. One corresponds to the output Alice gets. The other corresponds to the output Bob gets. And the way this is defined is that there is a simulator that simulates a view for any malicious Bob, or generates a simulated state row ideal, which is close in trace distance to the state that Bob would have obtained in the real interaction. And the way this is done in the computational setting, which is now going to be more, which is going to come up more in our analysis, is this notion of computational indistinguishability, which means if you had any quantum polynomial time non-uniform distinguisher D, then the probability that the distinguisher given row real said 1 would be very close to the probability that the distinguisher given row ideal said 1. Okay, so that's the guarantee that we will need. And similarly, security against malicious Alice can be defined in a very similar way. And there is this amazing result of Killian, which actually builds on this GMW, which is the protocol I was just talking to you about, where you secret share your inputs and evaluate this circuit. Killian showed that actually assuming OT, every two-party or even multi-party functionality can be computed in a maliciously secure way, just given black box access to OTs. And what I mean by black box is Alice and Bob just get access to OT black boxes into which they can feed their inputs and get outputs out of them. Now, the reason this is super interesting is because this establishes OT as the foundation for all of secure computation of arbitrary functionalities. And sorry, let me just, and just to give you a sense of how we know to realize these tasks in a classical versus a quantum setting, it happens to be the case that in a classical world, oblivious transfer implies, this is something that I already told you about due to a result of Killian. It implies multiparty computation. And the way to build OT is to use different types of public key encryption schemes with enhanced properties. The example I gave you going back a few minutes ago used random oracles, but you actually don't need them. So it turns out that under assumptions like learning with errors, which you heard about on Wednesday, and assumptions like Diffie-Hellman, which is an assumption that's classically secure but broken by quantum computers. Under these types of assumptions, either learning with errors or Diffie-Hellman or a bunch of other assumptions, you can build oblivious transfer protocols. And those imply multi-party computation. On the other hand, remember the one-way function primitive that I told you right in the beginning of the talk, which is a function that's easy to compute in one direction, but hard to compute in the other. There's this question of whether public key encryption schemes and oblivious transfer can be realized based on one-way functions was studied many years ago in this seminal work of Impaglia, Zhou, and Rurik, who showed that one-way functions cannot actually be used in a black box way to build OT protocols. And when I say black box way, I mean there cannot exist a construction that is oblivious to the exact description and the algorithm that the one-way function uses. Now, the question of whether one-way functions can be used in a non-black box way by an algorithm that makes use of the code of the one-way function somehow, this problem has remained open since then, and a lot of effort has gone into trying to answer it. It still remains unanswered, but many in the community believe that this is also not possible. We don't know how to prove it. It's believed that this is unlikely, but could be true. Yes?
Somehow inclusive, like, can we see why it's not possible in a black box way for one function to construct?
Do you want to see the proof of why that is difficult?
There's some intuition.
Right, okay, so good. And what is the second question?
The second question was, how do you even define non-black box? Because I thought one-way function is, by definition, a very abstract thing. So what would a non-black box with in general?
Right. So, okay, so let me answer both your questions. I was not planning to talk about why one-way functions do not imply oblivious transfer in a black box way. One of the reasons, I guess, is that oblivious transfer classically implies classical public key encryption, and that is already known to, like, the same result shows that actually public key encryption also cannot follow from one-way functions. Intuitively, super duper intuitive level, one-way functions and public key encryption are very different primitives because encryption schemes inherently involve trapdoors. The trapdoor is the secret key of the encryption scheme that lets you decrypt any arbitrary ciphertext that was created with respect to your public key. On the other hand, one-way functions are non-trapdoored primitives inherently. There's no single trapdoor that will let you invert the one-way function anywhere. So that's the structural difference between the two. Now, that does not necessarily mean that they're not the same, but it was possible, like this result did show that you cannot use one-way functions without referring somehow to the exact way the one-way function is built. So your second question, which brings me to your second question. The second question was, what does it mean to have black box, to make black box use of a one-way function versus to make non-black box use? The best way to think about this is, suppose I gave you black box tokens, hardware that allowed you to realize OT. That allowed you to realize one-way functions. So that means into the hardware box, you put some input X, and the box gives you an output Y. And I can guarantee you that nobody can reverse engineer this box to recover X from Y. But you don't know how the box works because it's a hardware box. You cannot actually open it and inspect its code. Then any construction that would work and would even work with this definition of a one-way function is unlikely to give you oblivious transfer. Now, unfortunately, most of the constructions that we have actually do work with black boxes for all primitives. So there's very few known ways to build objects that, okay, well, that's not entirely true. In this context, it is. Yeah.
I was just trying to ask, maybe we can discuss this afterwards, that if you use some non-black box property, then you're not building it from any one-way function, you're building it from a specific one-way function.
Right. If you use some specific property of the underlying assumption, then it's no longer a generic construction that uses any one-way function. What this rules out are generic constructions from arbitrary one-way functions. So for example, learning with errors implies the existence of one-way functions and also implies the existence of OT. Yeah. Now, things become dramatically different in a quantum world where learning with errors is known to imply OT, just like the classical setting. This was a result of Damgard et al. But one-way functions are also known, and they have been known for the past 12 years or so, to imply weak variants of OT. This started with a template introduced by Crepeau and Killian. It was built on by Bennett, Brassard, and others, and also Bowman and Fair. And there have been many other works in this line that have analyzed constructions of oblivious transfer that only start at one-way functions. However, the reason I say weak OT there is because they don't admit polynomial time simulators. So if you recall the simulation paradigm, we said there should be a simulator, it should produce this view for the adversary, and that particular simulator in these constructions is usually a super polynomial time simulation, or maybe there is no explicit simulation at all, but you can abstract out their ideas to build super polynomial simulators. So basically, the running time of the simulator is super polynomial. The problem with that is that just definitionally what that means is that anything that the adversary learns in the real game, the adversary could have learned with super polynomial running time in the ideal game. So it's saying that the adversary may learn a little bit more in the real game than they would have learned in their interaction with the trusted party. More precisely, what they learn in the real game is bounded by what they would have learned in their interaction with the ideal party, plus given more time to run. And so that's not ideal. In particular, it does not imply, is not known to, and it gets ugly if you try to get it to imply multi-party computation or nice composable versions of it. And yeah, so this is not known. And so after the break, we're going to look at how to use one-way functions to close this gap here and build oblivious transfer with polynomial time simulators, standard security guarantees, just only assuming the existence of one-way functions. And this is from 2 recent works that, of course, build a lot on all these templates from the literature. So we're going to talk about some of these older templates and then how to make some small changes, some changes to them to get oblivious transfer with polynomial time simulation, which implies multi-party computation with polynomial time simulation. I just want to say one last thing about this little quantum in the brackets here. So far, this talk was all classical world stuff. So the functions that we were talking about, the circuits we were looking at, were all classical Boolean circuits. But it turns out, due to these, specifically this work of Dulek and others, who showed that if you have a multi-party protocol that lets you evaluate general classical circuits, then it can be information theoretically compiled into a multi-party computation protocol that lets you evaluate arbitrary quantum circuits also. So the function f that the players want to evaluate could even be quantum, and even then, OT is the main building block that you would need. And OT would be necessary and sufficient. Okay, so that ends part 1. See you in half an hour, maybe a little more.